Now, this is the first lesson in our unit on energy. And what we're going to talk about specifically today is something called work. This is a concept that's really closely associated with energy. So it makes sense that we would sort of do a first lesson that talks a bit about both of them. But first, a bit of background on energy itself. Energy, perhaps the most important thing to know about energy, is it is something that cannot be created or destroyed, only transferred from one form to another or from one object to another. This idea of not being able to be created or destroyed is really important and really powerful. There are a few things in the universe we know of that can't be created or destroyed. Now, if you've taken a chemistry course, you've probably learned about a couple of these things. The ones you talk about in chemistry are mass and charge. Mass is conserved. It can't be created or destroyed. Charge is conserved. It can't be created or destroyed. And knowing those two things help you to balance chemical equations and help you to come up with formulas for compounds that would be neutral. So mass is something that can't be created or destroyed. Knowing that is a really powerful thing. Electric charge, positive and negative charge, is something that can't be created or destroyed. Knowing that can be a powerful thing. And there are other things we know of in the universe that can't be created or destroyed. Momentum, which you'll learn about later, is one of those things. And energy is perhaps the most famous thing in the universe that can't be created or destroyed. Now, other than that, we don't really know what energy is, at least not in the same way that we know what electric charge is. We know electric charge comes from things like, for example, protons that have a positive charge and electrons that have negative charge. And if I have some protons or electrons on an object, I'll give it a positive or a negative charge. So we kind of know what electric charge is. We know where it comes from. We can detect protons and electrons. But energy isn't like that. We can't, there's no particle that gives an object energy. So we can't see it or detect it in that sense. And we don't really know why energy exists or what causes it. At some point, we just kind of came up with a formula for calculating energy. And we realized that every time we calculated this number, we always got the same result, meaning it was always the same amount of energy. It wasn't created or destroyed. So you can almost think of it as something that we sort of stumbled on accidentally without really knowing where it comes from or what it truly, truly is. So in some ways, energy is a bit of a mystery in physics, but in other ways, it's a really, really powerful tool because we know it can be created or destroyed. Now, a little bit more about energy. So as you, I believe, have learned already, energy sort of can be sorted into two types. We call them kinetic energy and potential energy. So kinetic energy results from an object's motion. So whenever an object has motion, it has kinetic energy. And potential energy results from an object's location. So you can put an object in one location, that might give it potential energy. You can put it in a different location that might give it more or less potential energy. So we can figure out the potential energy of an object based on its location and the kinetic energy of an object based on its motion or its speed. One way to think about these two is I think of kinetic energy as being an object's speed, and potential energy is when an object has the potential for speed or the potential for motion. And we'll go through a few types of energy here to sort of illustrate this point. So these are a number of types of energy that you may have heard of before. And what I want to show you is that each of these types of energy here can be sorted into one of these two categories of either kinetic or potential. And in all of these situations, we either have something that is moving or we have something that has the potential to move. So gravitational energy is one example. A good way to think of this is you take an object, you lift it up above your head. It doesn't have motion at that point, but it has the potential for motion, that object you're lifting above your head. Because if you let it go, you know it's going to fall and it's going to start to move. So that gravitational energy that object has is a type of potential energy. Another example would be elastic energy. Imagine you have a slingshot. You load a rock into your slingshot and you stretch it back. You're sitting there holding the rock. That rock doesn't have motion, but it has the potential for motion. If you let that rock go, it's going to start moving pretty quickly. So that rock has potential energy. We can go through the whole list like this. Electric energy. Think about electricity that comes out of the wall socket in your home. If you plug a motor into that wall socket, the motor will start to move. There's some potential for motion here. Magnetic energy. This is also a form of potential energy. If you imagine taking two powerful magnets, putting them down on your desk, maybe a couple centimeters away from each other, you would expect if you let them go, they would quickly move towards each other. So there, again, we have potential for motion. And also to remind you that potential energy comes from location. If I put those magnets nice and close to each other, the location they're at means they have the potential to move pretty quickly. But if I put those magnets further apart in different locations, they might be less likely to suddenly move towards each other. That rock in my slingshot, right? It's because of its location, stretched back in that slingshot, that it has that potential energy. If I were to put it in a different location, say maybe I ease up the tension in the slingshot and I let the elastic in the slingshot just sort of dangle, now the rock's in a different location, it doesn't have that potential energy anymore. It doesn't have the potential for motion. So we get this potential energy by having things in certain locations. Another example of potential energy is chemical energy. Example would be in an explosive or a bomb that's about to go off. In a bomb that's about to go off, you have the potential for motion. That bomb goes off, things are going to start moving pretty quickly. And it's because of the location of all the different elements, the different atoms in that bomb, that there's going to be a reaction that's going to cause that bomb to go off. Now we're getting a little more interesting down here. Thermal energy. This is actually a type of kinetic energy. And you may recall that when an object has some temperature, is kind of hot, it's because on a microscopic level, it's the molecules in that object, the particles in that object, are vibrating back and forth very quickly. And the hotter the object is, the faster those particles, those molecules are vibrating. So thermal energy, when an object has temperature, it's actually because the molecules in the object are moving. So it's exactly an example of kinetic energy. Sound energy. You shout and your voice travels through the room. This one's weird. It's actually a combination of both kinetic and potential energy. Kinetic because as your sound travels through the room, the sound is sort of caused by air molecules vibrating back and forth. So there's some motion there. Those air molecules also are experiencing different pressures, different air pressures. And that air pressure kind of acts like a spring. So in that sense, it's kind of like this elastic energy or this potential energy here. And the last one I'm going to throw in here just to kind of make you think a little bit. The last type of energy I want to mention is mass. Now, okay, this one you might say doesn't really fit into my lesson here because it's sort of its own type of energy. We don't even often think of mass as a type of energy at all, but it is. And I mention this just to kind of pique your interest a bit. And if you take more courses in physics, you'll learn about the equivalence of mass and energy. It's fascinating stuff. But we don't normally say mass is potential energy or mass is kinetic energy. It's kind of its own third type of energy. And you might recall there's an equation, E equals mc squared, which tells us how much energy is in a certain amount of mass. But that's a complicated topic. It's a topic for another time. For now, I want you to just realize that every type of energy is either potential energy or kinetic energy. And potential energy is when an object has a certain location that gives it the potential for motion. And kinetic energy is when an object already has motion. Now, at this point in your physics careers, we want to improve your understanding of energy. And I want to give you a bit of a definition for energy, which you may not have really received up to this point. And at this level, the definition we're going to use is that energy is the ability to do work. And this is the topic that we're going to focus on for the rest of this lesson. What is work? Since it's crucial to understanding what energy sort of is, or how we're going to define energy in this course, we need to know what work is. So we have an equation for work, and it looks like this. So W equals F times D, and there's a weird little symbol here. Well, the W stands for work, the F stands for force, as we're used to, and the D stands for distance, as we're used to. Now, this extra symbol means parallel to. And so what this means in the context of this equation is that if we're trying to calculate work using a force and a distance, we need to make sure that the force and the distance are parallel to each other. So, for example, if an object feels a force that's up, and it moves a distance that's also up, then those two are parallel, and it will have some work done on it. But if an object feels a force that's up and it moves a distance that's to the right, well, up and right are not directions that are parallel to each other, so there wouldn't necessarily be any work in that situation. More on this later. Okay, how about the units in this equation? Well, you're pretty familiar with the units for force and the units for distance. Those are going to be measured in newtons and in meters. And so we can figure out pretty quickly what the units for work are going to be. If work is force times distance, then the units of work are going to be the units of force times the units of distance. So newtons times meters, or Newton meters. Now, because we use this unit a lot, we've actually given it a new name, and we've named it after someone who did a lot of pioneering in this area of physics. And his last name was Joule. So going forward, instead of saying Newton meters as the unit for work, we're going to just say joules. This actually might remind you a bit of the unit Newton to start with. You might recall that we have another name for newtons. They're called kilogram meters per second squared. But it's kind of a mouthful. And there was a guy called Newton who did a lot of work in that topic. So we sometimes call a kilogram meter per second squared a Newton in honor of him. And for that same reason, we sometimes call a Newton meter a joule in honor of this guy. Now, one of the things that's really useful about work is that work is a scalar, as is energy. This means it doesn't have direction. It has magnitude, but not direction. This means it can be really easy to work with. You don't have to worry about drawing vectors and thinking, is this right? Is this up? Is this down? Is this at some weird angle? So it can make solving complicated problems a lot easier using work and using energy. However, even though it's a scalar, it doesn't have direction, it can still be negative or positive. And what would make it negative is if F and D are anti-parallel. And by anti-parallel, I mean in opposite directions. So for example, if the force on something is upwards, but the distance that thing moves is down, we would say that force and that distance are anti-parallel, and there would be negative work done on that object. So imagine you are trying to hold an object in the air, but it's too heavy, and you're slowly losing that battle, and it's slowly falling down, down, maybe not falling, but getting lower, down, down, down towards the ground. You're doing your best to lift it, but it's just too heavy. The force you're exerting is up, but the distance the object's moving is down. So in that situation, F and D are anti-parallel, and we would say that the work you are doing on that object is negative. Another thing to know about work is work is the transfer of energy to a different object or a different form. Whenever work is being done, it means energy is either going from one form to another, maybe from potential to kinetic, or it means energy is going from one object to another. So work is kind of like the movement of energy. I want to take the example I was just sort of talking about and push it a bit further. So think about when you hold an object in the air. So this time you're strong enough to actually keep it in one place. Maybe you find it a bit heavy. It's a bit difficult, but you're able to hold it above your head. If you do that, do you do any work? And here's a situation where maybe our everyday use of the word work is a bit different from how we would use it in physics. In everyday language, if you told me to hold a heavy object above my head, I might say, yeah, I can do that, but that's tough work. It's a lot of work for me to do that. In physics, we wouldn't necessarily say that. Because in this situation, no work is done on the object because the distance it moves is 0. So looking back at our equation here, if I am just holding an object above my head, yeah, I'm exerting a force on it upwards, but the distance that object moves is 0. So even though I'm kind of struggling, I'm having a hard time, I'm not actually doing any work. At least I'm not doing any work on the object because the object isn't moving, in the physics sense of what work is. So students sometimes have a hard time with this. How can you tell me that I'm not doing any work when I struggle to hold this heavy object above my head? Well, the key thing is in physics, you got to be clear about what object is doing the work and what object it's doing the work on. So why does it feel difficult when you do this? The answer I'll give is because in order to hold that object above your head, your heart has to pump your blood. And you might find your breathing rate goes up. Your lungs are working hard to get enough air in and out of them. So inside your body, there is kind of work that's being done. Your heart is pushing on your blood. Your heart is doing work on your blood. Your lungs are doing work on the air by pushing it in and out. Your blood and the air are moving. They're covering distances. But that actual object that you're holding in the air, it's not moving. So no work is being done on that object. This is a bit of a weird concept for people to wrap their heads around, but if you just think back to this equation, in order for work to be done on an object, that object needs to move a distance and feel a force that is parallel to that distance. Okay, so let's do another example, this time with a few numbers. Imagine you lift a 30-kilogram weight from the ground to a height of 1.5 meters at constant velocity. And by now, when you guys see this phrase here, you should think, yep, that's going to be important. And it is. How much work do you do on the weight as you lift it to this height at constant velocity? Well, let's do a little free body diagram. There's my weight. I've got a gravity force down, and I've got a force from me pushing it up. And because it's at constant velocity, I know these two forces must be balanced. So that gravity I can calculate right away. It's going to be 294 newtons. Then I know that this force from you lifting the weight is also going to be 294 newtons. Okay, so how much work do you do on the weight? Well, let's start with our formula for work. Work equals force times distance, but they have to be parallel. Well, the force that you are exerting is 294. And the distance that the weight moves is 1.5 meters from the problem here. Then I just have to make sure that those two are parallel. That tells me that I actually can use this equation. Are they? Well, the force that you're exerting is up. The distance that the weight moves is also up. So yes, those two are parallel. That means I can continue, and I get an answer of 441 joules. That's how much work you do on the weight as you lift it up. Here's a follow-up question. How much work does gravity do on the weight? Well, let's tackle it again. Work is force times distance. Only this time, because I want to know the work being done by gravity, I'm going to use gravity as my force rather than you as the force. So gravity was also 294 newtons down here. The distance the weight moved was still 1.5, but then I got to check this parallel thing. Are this force and this distance parallel? Well, the object is still moving up. 1.5 meters is the distance, and that's up. But gravity, even though the object is going up, gravity is pulling down. So this 294 newtons is down. So here I have a case where my force and my distance are up and down. And what we would say about those two is are they parallel or not? Well, they're parallel in the sense that they would never cross, right? A line going up and a line going down would never cross. But they're not going the same direction. And here's where we would use that word anti-parallel. One's up, one's down. They're anti-parallel. So what that tells me is, yes, I can use this, but I'm going to have to throw in a negative sign at the end. You'll recall we said up here, if F and D are anti-parallel or in opposite directions, work can be negative. So that's where that negative sign comes in, right at the very end. We just toss that in, very last thing, because we realized that these two, that force and the distance, were anti-parallel or in opposite directions. Okay, so we've done one example where F and D were parallel, and we just plugged numbers in and it was great. We've done one example where F and D were anti-parallel, so we plugged numbers in and then had to throw in a negative sign at the end. Now we're going to do one example that's a little more complicated still. A stubborn poodle refuses to walk. His frustrated owner drags the dog back home along the 11-meter driveway by its leash. If the leash makes an angle of 35 degrees with the horizontal and has a tension of 90 newtons, how much work does the person do on the poodle? Okay, let's start with a quick diagram. There's my poodle. I've added a collar to him. We need something to attach the leash to. Here's the driveway, 11 meters long, that poodle is going to get dragged along because he's refusing to walk. And let's look at some of the forces here. So I want to know how much work the person does on the poodle. So that person is exerting a force on the poodle through the leash. So let's draw that. There's the force coming from the person. It's a tension force because it's sort of acting in this leash. And that is 90 newtons. And we said it was at a bit of an angle. So I've drawn it at an angle here. So this person is pulling in this direction, and the dog gets dragged up the driveway horizontally, like that. Now, right away, you can see this is maybe going to be a problem because the force is going in this direction, up at an angle. The distance the dog moves is straight to the right. So those two are not parallel. They're slightly different angles. Now, I want to bring you back to our previous unit on motion, where sometimes we dealt with vectors that were going in weird directions. They weren't just up, down, left, right. We would use directions like 35 degrees to describe where they were going. And one of the tricks we had for dealing with vectors that weren't in very nice directions is we split them into components. So what that looks like here is I say, okay, here's a weird vector at an angle. Let's replace it with one vector that's horizontal and another vector that's vertical. The idea is I like things that are horizontal and vertical. Those are easy to work with. So let's get rid of this guy the hypotenuse here, and let's replace it with one that's horizontal and one that's vertical. And the idea is this plus this gives me that. So I can ignore that 90 and use these two components instead. So if I'm going to be working with these components, I should probably know what they are. Here's where your trigonometry is going to come in useful. And you use SOHCAHTOA to help you with this. I won't do a review on that right now, but to find the length of this side, it's going to be 90 times the cosine of 35 degrees. That'll give you 73.7 newtons. And to find the length of this side, I can go 90 times the sine of 35. And that'll give me 51.6 newtons. So those are the magnitudes of my components of the tension force. OK, so let's get back to this problem. We're trying to find out how much work does the person do on the poodle. Well, work is going to be force times distance, but they have to be parallel. And here I'm going to say, OK, well, I've got a bunch of different forces now to choose from. I've got a 90, a 73.7, and a 51.6. Which one am I going to use? Well, I'm going to use the one that's parallel to my distance. Right? I can only use this equation if my force and my distance are parallel. I know my distance is to the right. So which of these forces is parallel to that? This one right here, my 73.7. This one, we actually decided we were going to ignore it completely anyways. When we drew these components, we basically got rid of that one. And this one is not parallel at all to this distance. This one is perpendicular to the distance. That's about as far away from parallel as you can get. So this guy is doing absolutely no work while the dog moves that way. This guy is doing the work. So I know the distance is to the right. I have to pick a force that's parallel to that. So I pick the force that's going to the right. That's my 73.7. Then I multiply those two together, and I get 811 joules is the work done by the man or by the leash on the poodle as it's dragged up this driveway. So a quick reminder I like to do at the end of this lesson is if your force and your distance are in the same direction, work is positive. If your force and your distance are in opposite directions or they're anti-parallel, work is negative. If your force and your distance are perpendicular, like we had here where we had the distance was this way, but this force here was that way. So if force and distance are perpendicular, no work is done. And if your force and your distance are kind of at an angle, like we had originally in this question with this 90 at an angle and my distance there, then we break it down into bits and we use components to figure out the question that way. That's a quick review on how to calculate work. Give the problem set a try, and we'll see you in the next lesson.